Welcome back to the deep dive. Today we're taking a huge stack of technical sources and we're really distilling the absolute essentials. This is for anyone who's navigating that convergence of networking and DevOps. We're hitting the critical foundational knowledge points, the concepts that really underpin how modern networks are built, configured, and monitored automatically.
That's right. If you're listening, you're probably looking for a shortcut to being really well informed on the architecture of network automation. We're synthesizing knowledge points that range from, open source tools like Ansible, modern data structures like Yang, all the way through to new protocols like JTI and gNMI.
So a structured tour.
Exactly. Think of this as a structured tour of the automation lifecycle. We're pulling out the 10 most crucial technical nuggets you need to understand right now.
Okay, let's unpack this. Let's start with the development side. When network engineers start automating, they immediately run into the problem of scale. They write a perfect playbook for one task, but then they realize they need to write 100 more. So the challenge is, how do you avoid rewriting basic stuff, like configuring NTP or AAA every single time? Where does the network community, pool its reusable resources?
That centralized hub is Ansible Galaxy. It is the community content repository where users publish, browse, and download Ansible roles and collections.
I sort of think of it as the app store for configuration modules.
That's a great way to put it.
But what does using Galaxy actually provide, beyond just convenience? Is it about reducing custom code, or is there a standardization benefit here?
It's both. The primary value is accelerating development and easing standardization. Look, if you're building a large automation platform, maintaining thousands of lines of custom code is a nightmare. Galaxy lets you integrate community-vetted roles for common tasks.
Which means faster development.
Faster development, and crucially, less testing overhead on that common functionality because the community has already done the heavy lifting. Content reuse is the key efficiency driver here.
Fantastic. So we've written our playbook, maybe pulling some roles from Galaxy. Now we need to deploy. And the gold standard for deployment is zero-touch provisioning, or ZTP. The goal is simple. Plug a device in, and it gets its config automatically. But before any custom scripts or configuration files are pulled down, what is the absolute first protocol step that a factory default device has to execute?
It's the initial handshake. And it's the protocol that everyone overlooks because it's just so basic. DHCP.
DHCP, really? Yeah. Not just for getting an IP address?
Exactly. The factory default device uses DHCP to automatically get two critical pieces of information. Yes, the IP address, but more importantly, the location of the configuration server or the boot script URL.
Just pointing the way.
DHCP options are used to point the device to the next stage in the provisioning chain. Without that initial DHCP success, the whole ZTP process never even starts.
That makes perfect sense. DHCP is the initial map reader. Okay, let's talk safety. We're moving toward these large-scale automated changes, and the fear of taking down, 50 devices with a single typo is very real.
Mm-hmm.
If I'm using Ansible to roll out a massive configuration update, how do I run the playbook to verify its logic and see exactly what it would change without actually applying a single modification?
That safety measure is Ansible's check mode. You activate it using a command line option, the check flag.
The dry run.
The dry run, exactly.
So it does all the logins, it validates the modules, it checks the logic, but it just stops short of that final commit.
Precisely. Its primary value is mitigating risk. It lets you validate the configuration logic against the current state of the device and verify all potential impacts. It shows you what would happen.
Right.
This is essential for, governance and compliance. You ensure changes are safe before that final commitment to production.
Mm-hmm.
It's your last line of defense.
That transition from theoretical dry runs to actually managing configuration and ensuring it's functionally correct, that's a perfect bridge to our next section. Structured data, modeling, and testing. Because after we apply the config, we need to prove the network is actually behaving correctly.
And testing is arguably the most difficult cultural hurdle in network DevOps. It's not enough to verify the configuration applied. You need acceptance testing to verify the resulting network behavior. Did the BGP session come up? Is the API returning the right status code?
Okay, for this acceptance testing layer, what open source framework has really gained traction in the network DevOps space? Something known for its simplicity and flexibility.
That would be the robot framework. It has become incredibly popular for network environments.
And what makes it the right tool for engineers who, might be comfortable with Python but hate writing complex unit tests?
Its defining feature is its Human-readable, keyword-driven testing syntax.
Human readable, okay.
You don't need deep programming skills to write comprehensive test cases. You can create tests using high-level keywords like check BGP neighbor state or verify API response 200. This approach makes it super accessible. It bridges the gap between traditional network engineers and software testers, letting teams build automated verification quickly.
Okay, so testing validates behavior. But a lot of our automation relies on pulling operational state data from the device after a change. When scripts pull structured output from Junos, that output is often in XML format, which is messy. It's deeply nested. If I only need to extract the interface stats for, say, port GE001, how does my script efficiently navigate that huge XML tree to pinpoint just that one piece of data?
You need a language designed specifically for traversing complex hierarchical data like XML. And that standard is XPath.
Expressions.
Yes, XPath expressions allow your automation scripts to accurately locate specific nodes, elements, and attributes within that structured XML output. Think of it like GPS coordinates for your data. Without XPath, you'd be forced to use messy text parsing tools like grep or regular expressions, which are brittle. They break easily if the output format changes even slightly. XPath ensures reliable data analysis.
That's the parsing side. But XPath only works because we're dealing with structured data to begin with, and that brings us to Yang modeling. Yang is what defines the configuration programmatically. If I define a list in a Yang model, say a list of firewall filters, how do I ensure every filter I add is unique and can be consistently referenced later? How do I prevent duplicate entries?
This is a fundamental concept of structured modeling.
Yeah.
You must use the key statement.
The key statement, why is that so vital? Beyond just, preventing duplicates.
Well, the key statement specifies the field or combination of fields that uniquely identifies each entry in that list. Its importance is tied to transactional integrity and idempotency.
Idempotency, right.
If you want to modify or delete a specific firewall filter, you need a reliable way to reference that exact entry. If you don't define a key, the data model becomes ambiguous. That consistency is essential for automation tools that need to reliably merge configurations or ensure the same playbook run twice gives you the exact same result.
We've covered the tools for development, safety measures for execution, and the data structures for configuration. Let's move to how the device actually interacts with the code. Section 3, modern interaction and telemetry.
Let's start on the device itself. A lot of engineers write custom operational or event scripts, sometimes Python, sometimes XSLT, to run directly on the network device. If I write a script like that, where must it reside in the Junos OS file system for the system to recognize, load, and execute it reliably?
There is a required location, right? It's not just any temporary directory.
Exactly. The default and required execution directory is vard scripts.
Okay, why that specific path? What's the strict requirement for?
That directory is critical because it ensures the scripts are properly indexed, loaded into memory, and executed within the secure, defined context of the system's automation engine. If you put them somewhere else, they just won't be indexed. The device won't be able to call them reliably. It's all about maintaining security and stability for on-box automation.
Stability is paramount. Okay, let's look at external control, specifically using Junos PyEZ, which is the Python library for managing Junos devices. When I use PyEZ to programmatically push a config change, there's a moment of vulnerability where another user or another process could try to push a conflicting change at the same time. What critical method must my script call first to ensure I have exclusive control over the configuration database, to guarantee my transaction integrity?
To maintain that transactional consistency, you have to initiate your change sequence by calling the lock method.
So if I don't call lock, I risk a configuration race condition.
Precisely. The lock method obtains an exclusive lock on the configuration database. This prevents any other user, whether it's a human on the CLI or another automation script, from modifying the configuration at the same time.
It's like a do not disturb sign.
It is. It's the programmatic equivalent of putting a do not disturb sign on the configuration until your commit is complete. It prevents those conflicts and ensures data integrity.
This need for programmatic control brings us to monitoring. The shift from manual config to full automation is mirrored by the shift from polling to streaming data, which is telemetry. So what's the fundamental architectural difference between the traditional, decades-old SNMP approach and the modern Junos telemetry interface, JTI?
The difference is defined by who initiates the data transfer. SNMP relies on a pull model. The monitoring system periodically polls the device, asking, what is your data now?
Yep.
JTI uses a push model, where the device continuously streams data to the collector without being prompted.
Okay, but polling has worked fine for 20 years. Why the radical mandatory shift to push? Is it purely about frequency?
Frequency is part of it, for sure.
Yeah.
JTI gives you much higher data granularity and lower latency. But the biggest reason is scaling and efficiency. When you have thousands of devices, constant polling, that poll model puts a heavy, unnecessary CPU load on every single network device.
Just waiting to be asked.
Just waiting for the next request.
Yeah.
The push model offloads that burden. The device efficiently streams the data, often only when the metrics change, and that dramatically improves scalability. It allows for real-time operational awareness, which is essential for detecting things like microbursts or sudden network anomalies.
So the push model is really a necessity, not a luxury?
That scale, yes.
And if we're using modern protocols for streaming, like gNMI, we need a way to ensure our management system and the device are, speaking the same language. Before I start a subscribe or get operation to stream data, how do I programmatically verify which data models, like OpenConfig or custom Yang models, and which encoding formats the device actually supports?
To validate that compatibility up front, you use the capabilities RPC.
The remote procedure call that reveals the device's identity and abilities, like asking for its resume.
Exactly. This operation is essential for robust automation. By calling the capabilities RPC, your client system can discover the full range of supported Yang models, versions, and data encodings. This ensures you only request data the device is capable of providing, preventing interface failures, and making sure that complex gNMI operations like get, set, or subscribe work reliably the first time.
If the technologies we discussed today, structured data modeling like Yang and streaming telemetry like JTI, are now mandatory for scaling, how fundamentally does this change the required skill set, transitioning the modern network engineer from being primarily a command line operator to becoming a sophisticated software integrator? Think about that as you implement your next automated change.